Hello and welcome. My name is Adam Feinstein, and I am the LED Product Manager for the AFM business in Bruker. I would like to welcome you to this installment of the Bruker AFM webinar series. This presentation is titled Atomic Force Microscopy in the World of LEDs, presented by Stefan Kamer. Before I introduce Stefan, I would like to make a few quick logistical comments. First, we encourage your participation during the webinar, and if you have a question, please type it into the questions dialog box on your screen. We've already had a couple submitted. We will accumulate these questions throughout the presentation, group them together, and then answer them at the end of the prepared remarks. Quite often we have more questions than we can answer in the session, and in those cases we will be sure to follow up with answers via email afterwards. Also, if you would like to review the presentation afterwards or pass it on to a colleague, the webinar will be posted online within 1 week in the webinar section of the Bruker webpage. As a follow-up to this presentation, you will be receiving an email with this link. Finally, when you exit the webinar software, you will be asked to take a brief survey. We would very much appreciate it if you would take the time to complete this, as it helps us pick the topics that are most important to you and to generally make this series better. So let's get started, and let me introduce our presenter, Stefan Kamer. Stefan earned his master's in chemistry and PhD in physical chemistry in 1992 from the Technical University of Braunschweig in the group of Professor Lochmann. He started working in AFM as a scientist for topometrics in Europe in 1993. Before coming to the US in 1995, Stefan lived in Japan working as a guest scientist for Hitachi in the field of near-field optics and phase change materials. Since 1995, Stefan has worked for Veeco in various technical management and product marketing roles. Currently, Stefan is a senior member of Bruker's application development staff in Santa Barbara, California. So let me now turn it over to Stefan for his talk entitled Atomic Force Microscopy in the World of LEDs.
Yeah, hello and welcome from Santa Barbara to our webinar today about atomic force microscopy in the world of LEDs. When we looked at the participant list for the webinar, we found quite a varied audience, not the usual AFM audience. So what we did therefore is we outlined the webinar as follows. We will start with an introduction to LEDs, talk about applications in display and lighting, and then just to get the our participants from the LED side up to speed, we will introduce just very briefly atomic force microscopy and imaging modes. We will then go ahead and talk about OLED applications, surface morphology and electrical measurements, and then just before the conclusions, talk about solutions for industrial environment, highlighting productivity and automation. Performance depends on controlling the nanoscale, and AFMs are, of course, the tool to achieve that goal. I have basically the variety of applications in the LED world on the slide here, and throughout the talk I will show you a bunch of recent examples from the literature, so not to be too dependent on what we did here in-house. So let's start on the top left. Graphene oxide. Graphene, of course, is a very hot material these days, and graphene oxide has found its application into the OLED world. We will talk about that. Of course, the AFM here is used to visualize the surface quality of the layer. Device performance on an LED depends on injection efficiency. How effective are carriers injected from the electrodes into the into the stack, and that of course puts a critical emphasis on the quality of the electrical contact. What's shown on the bottom left here is a paper that dealt with mapping current density versus voltage, and allowed the researchers then to determine spatial variations on the nanometer scale in terms of contact quality. And they simply did it by basically mapped current density versus voltage curves in a similar way. In a standard AFM experiment, you might map force volume curves and then fit it to a modified Mott-Gurney equation, and then they can figure out if you have an ohmic contact or a non-ohmic contact. And of course, experiments like that are when they deal with heterojunctions, in this case on organic semiconductors, they're applicable not only for LEDs but also for organic solar cells. Now when we go to the middle top diagram, the LED itself is not the whole device, of course. Somehow you have to address the pixel, and what's often used is a TFT. So on these transistors need to be understood, and one way to understand them is to perform, for example, Kelvin microscopy measurements on it. And that's an example that we will talk about that deals with that, where researchers investigated the transport mechanism in these TFT transistors using Kelvin probe microscopy. And then, of course, on the right, classic metrology application that probably put the AFM on the map. The example we choose here is a pattern sapphire structure in high brightness LEDs, and you can see the surface of the pattern structure in the image shown here. And then the bottom, of course, roughness measurements. In this specific case here on an oxide is again one of these classic applications that AFM is used for. And again, all these measurements are carried out with a nanometer spatial resolution, and that's what distinguishes the AFM from other tools that can do at least part of these measurements too. Now let's talk about AFM. The beauty of an AFM is that nearly any phenomenon that you can find can be somehow transferred and confined to the nanoscale when you use an AFM. And of course, the classic example is that you can image atoms directly, because there simply is no diffraction limit as in other techniques. It works a quite simple way. You have a sample, as it's shown on the top left diagram, and a sharp tip, and you move sample and tip relative to each other, and then there will be some interaction, and you bring the tip and the sample close to each other within atomic distances typically, and there's some interaction, and you can measure that interaction with a mechanism. Often a light lever is used, so the tip is simply attached to a cantilever, which is a spring basically, and you measure that deflection of the spring and then feed it into a computer system and extract the necessary information. The tip can be operated in several ways. The most state-of-art way is to move the tip up and down at sub-resonance frequency. It's a mode that's called PeakForce tapping. It's shown on the top right here, where not only can you do imaging, but at the same time you can extract a bunch of quite useful nanomechanical information while you do your imaging process. Of course, I already mentioned you can measure a variety of phenomena at the nanoscale, such as work function in this case, conductance, capacitance, doping maps, and so forth. I already mentioned PeakForce tapping. What is PeakForce tapping? PeakForce tapping basically uses the most basic operation of an AFM, and that is simply moving the tip up and down. And we call that executing a force curve. What happens during a force curve is shown on the top left diagram. Let's move the tip towards the surface as indicated by the blue arrow. So and the curve basically shows here the deflection of that cantilever. So in the beginning, nothing is going to happen. Your cantilever is not going to get deflected because your tip simply doesn't see any interaction between itself and the surface. And then at one point, there will be some attraction. So the cantilever will bend downwards, as we can see on the curve here. And then the tip contacts the surface, and the cantilever bends up. And then when we pull back, quite the opposite happens. The cantilever bends the other way, and at one point, the attractive forces between tip and sample are overcome by the spring force, and the cantilever simply jumps back into its original position. Now, when we have one of these force curves, we can extract a variety of information. As it's shown here, we can extract nanomechanical maps. We have a precise force control because we can lock on what's labeled here as the peak force for our imaging process, and we can address a wide variety of physical properties with a specific mode. We can also combine it with something that's called Scan Assist, and that allows us to do simple, consistent, high-resolution imaging. We can do very gentle imaging, and that increases, of course, the lifetime of your tip and consequently the cost of ownership. And it has significantly less artifacts than older AFM modes. One example of a PeakForce Q&M measurement is shown on the right here. It's a polymer system consisting of 3 components. And I indicated the 3 components in the topographic map shown on the left, A, B, and C. And on the right, you can see the modulus map that got extracted from the PeakForce stepping imaging process. You can clearly see the 3 components showing up with a distinctive modulus in this case. Okay, my computer seems to have a small issue here. Just apologize for a second. Okay, AFMs are not only devices to give you pretty images, even though some of these images do look quite pretty indeed. They're actually verifiable against traceable standards. So they're gauge-capable devices, and that in turn enables you to do high-fidelity metrology. And one example is shown here. What's shown on the top left is are the results of 30 images of VLSI, so a traceable standard with different step heights, and you can see the fit versus the AFM measurement is very, very good. And of course, that then allows you to do proper metrology. For example, on a TFT transistor here, where the part of the image and the cross section is shown at the top right, and you can see the topographic feature of the source drain, and of course of the a-IZGO channel separating the source and the drain here. Samples can be analyzed directly. There's no need for vacuum or cross-sectioning, and you can measure samples directly on a wafer if your instrument supports that sample size. Now let's go to an OLED stack. Shown a typical OLED stack on the left, and the first thing you will see is that the layers are quite thin, in the range of like 20, 30 nanometers or so. And that, of course, makes the control of the morphology of these layers so critical. because morphology and the electronic properties are strongly related here. And an example of an AFM measurement of two of these layers is shown on the right here. And the typical parameter that you find in the literature that people extract from AFM measurements are indeed the roughness number of the surface to give a quantitative measure of the quality of the surface. And once you do that, you can of course then use the AFM to provide instant feedback to optimize your process. This example here shows a setup of a generation 2 size OLED system, and during setup, these researchers used an AFM to characterize, in this case, the electrode, the ITO, and the anode and the cathode, to optimize the deposition parameters. And what you see on the right here is one of these data sets they use to optimize the process. It's an image of the ITO electrode. And again, they used the roughness calculation, which the AFM tool provides you in an automated manner to optimize their process. Now, what you do when your films, especially organic films, are too rough? Well, what's often employed is people anneal these films, so they basically heat treat them. And the example of such an experiment is depicted in slide number 9 here. So on the left side, we have the morphology of a OLED film before, and next to it post-anneal, and you can see the reduction in roughness by almost a factor of 4. And what that then does is shown on the right side. When you pay attention to the curves labeled A and D, you can clearly see that the device performance, so the current density, greatly increased with the when looking at the post-annealed film. So, so again, there's a direct proof that surface morphology directly correlates with the device performance here, and allows you to draw the conclusion that the morphology should be flat enough in order for carriers to be well injected and transported. Now, ITO is not the only electrode, and there's a variety of research out there in the field to come up with alternative electrodes. An example is shown here. It's a zinc sulfide silver multi-layer structure as a replacement for an ITO electrode. And again, it was concluded that the surface morphology has to be flat enough for carriers to be properly injected, and roughness again was used as a parameter here. So the researchers started originally out with a film that's about 2.3 or so nanometer rough, and then went on to less than 1 nanometer, and then found that if the roughness is below 2 nanometer, then the whole injection was close to optimum for their specific setup. Now let's go from roughness to electrical measurements, and one of the probably best suited modes for LED research is Kelvin probe microscopy, because it allows you to do quantitative work function mapping on the nanoscale. So how does it work? Let's look first at the diagram labeled 1, 2, 3 on the top left corner. So when two conductors are brought into electrical contact, for example, with an external wire, electrons will flow from the one with the lower work function to the one with the higher work function, equalizing the Fermi energies and consequently. So, and if you make them into a parallel plate capacitor, you will have opposite charges on the surfaces. Now, the potential established between these two surfaces is called the contact potential difference, or CPD, and that equals the work function difference of the two materials. Measuring the contact potential difference or work function is quite simple. You simply explain external potential as it's shown in diagram number 3 there, and you change that potential until the surface charges disappear. And in this case, your backing potential equals the work function, and that's exactly what you do in Kelvin probe microscopy. The setup for an AFM looks a little bit more complicated, as it's shown on the left side. At the bottom is our typical AFM setup, and then on the top of it you have the add-on for Kelvin microscopy, which basically consists of a set of lock-in amplifiers and additional feedback that can vary the backing potential that you apply between the surface and the tip to zero out that potential difference and then yield the Kelvin potential. State-of-the-art method for that is called frequency modulation Kelvin potential, because it allows you to with about 90% accuracy or so, to get actually a resolution of about 10 to 50 nanometers, whereas the older techniques of amplitude modulated KPFM are in the micron range if you want to see quantitative measurements. An example is just to verify performance is shown on the right here, where we have a aluminum silicon gold layer, and we can see at the bottom the cross section through it, and clearly see the various contact potentials of the three materials indicated. Now let's go to a photovoltaic device here. Again, organic photovoltaic devices and OLEDs are very similar, and a lot of the methods are, if they're applicable to one, they're applicable also to the other one. So what we did here is we performed some PeakForce KPFM measurements on an OPV in order to study the electrical response when we illuminate the device with light. In this case, we use 300 suns with an sun simulator. And that's what we get. So you get height adhesion. Remember, we use PeakForce tapping experiment, so we always get nanomechanical properties at the same time. And on the right, we see the potential. In the middle of the image, the light was changed from being on to off, and you can clearly see your device responding as judged by the change in the work function signal here by about ½ volt. And that's of course great, because it allows you to monitor device performance on the nanoscale. Now let's come to the transistor example that I showed you on in the beginning on one of the introductory slides. So amorphous semiconductors are used as transparent backplanes to drive the pixels in an OLED or on an LCD display. And one of the things that is important to understand is what exactly is the charge transport mechanism of one of these devices. And if you want to find that out, you actually have to somehow measure the density of states. Often you can, when you have a transport mechanism, you can extract the density of states as a fitting parameter. But in this case, we want to understand the density of states, so we have to measure it independently. And again, Kelvin probe microscopy can be used to do that here. So when we look at the diagram on the right here, we see a silicon gate on the left and the oxide channel, and then the AFM tip on the right. So when there's no electrical field presence between the gate and the channel, of course no charges are accumulated and the energy levels are represented by the solid black lines in the diagram. When we apply a bias to the gate, but at the same time keep source and drain at 0 volt, then of course an accumulation layer is formed in the a-IZGO channel in this case, which fills the conduction band. And of course, because source and drain are fixed at 0 volt, the Fermi level cannot move. So what has to happen is that the conduction band has to shift to lower energy. And of course, that shift is directly accessible with the Kelvin probe microscopy, and then consequently allows us to calculate the DOS and then come up with a transport mechanism. Now come to the graphene oxide example here. Performance of LEDs is largely dominated by the charge injection, of course, from the electrodes, and ITO is widely used, but for a number of reasons, not the most ideal anode material. And one of the reasons is there's a large hole injection barrier with the organics due to a mismatch in work function of the ITO and the energy level of the organic layers. And in this specific experiment here, graphene oxide was used as a hole injection layer. Graphene oxide has, for printable OLEDs, of course, also the advantage that it's a solution processable and, of course, quite easily chemically tunable. And what we see on the left is the AFM used to characterize the various graphene oxide layers that were prepared on the ITO to form the LED that was then tested. And when we look at the bottom table, so under anode, so we first start out with the reference ITO, and we find a maximum luminescence of 25K, and then when we add the graphene oxide to aid the hole injection, we can see a dramatic increase in luminescence at the various concentrations of graphene oxide used. And of course, at one point you run into the problem that you inject more holes than you inject electrons. So then what was also done is that not only the graphene oxide was added, but also the electron injection layer was modified. And you can see at the bottom here that even with 0.1 milligrams per milliliter graphene oxide, we end up at a maximum luminescence of 53.5K or so. So great experiment. And again, AFM is absolutely critical to verify the quality of these quite thin layers. Now, what can AFMs do, or what do AFMs do to support LED production? And of course, when you go into LED production for organic LEDs, of course you want to print or spin coat your devices. You don't want to. It's very difficult to vacuum deposit very large devices, or it's not very cost effective. So, but your AFM has to also keep up with it, and that's where our FastScan system comes into play, which is about 100 times faster than a conventional AFM, and this makes it suitable for production environments. It also has quite a lot built-in automation, and of course scan assist that we already talked about in the beginning. And then performance-wise, we have a very low drift closed-loop scanner here to still enable you the ultimate resolution on that system. Just to give you an example, that FastScan system is suited for industrial applications, but we can still get true atomic resolution on that system, as we have shown in data in one of our previous webinars. So it's quite a remarkable system. I'm going to show you now a video of a set of samples run on the FastScan system. So you see the operator here loading a sample on the left side will be 3 video views. The whole system, just the stage and the scanner, and then a video view from inside the system. So samples are loaded, and an automated imaging process is initiated, and the operator can now walk away and do his emails. So we can see the system is engaging now. It automatically adjusts feedback parameters, and we can see the first image coming up here. The actual time is displayed at the bottom left corner. So in this case, it's a block copolymer sample. Okay, got the first image. The tip is withdrawing. The stage is moving to the next location, engaging again. Feedback parameters are automatically optimized. We scan the next sample. So we made this actually a little bit more complicated. Instead of just scanning like a bunch of locations on one sample where you would say, oh yeah, once I figure out what my feedback parameters are, I don't have to change them anymore. We actually choose a variety of samples for the specific video. The last sample shown was CellGuard, which is a battery separator membrane. Again, we are up with sample number 3 here. And all these images are 512 by 512 pixels. Again, we have a polymer here, and these stripes that you see, this linear pattern, is not noise. That's actually really the polymer, the 25 nanometer periodicity. Yeah, FastScan is quite a dangerous instrument, so we encourage you, of course, to come visit us and demo it, but be aware that once you see it, you really don't want to use your old AFM anymore. So once you get used to the speed, you don't want to go back. Okay, the next sample here is something very flat, demanding in terms of noise performance. It's a mica surface where we can see some atomic steps and islands that are etched away. And then the last sample is a biological one. It's collagen fibrils. You can see the network of fibrils on the left, so the tip has absolutely no problem engaging and scanning this network. You can see these little bands, which are about 65 nanometers or so. Okay, so you've seen that in this short amount of time we scanned 6 different samples in a fully automated fashion. And now let's apply that to some relevant samples. And the example I have here is from the data storage industry. And the reason why I have that here is Bruker is dealing with metrology applications and semiconductor and data storage for a long time. So we have quite a breadth of experience in that field. And even though OLEDs are different samples, the application is the same. So that's why I'm showing you a couple of examples here. So what we've done here is we imaged a disk as it's shown on the left side, and we did 4 runs on this disk and we imaged it at 8 different angles. You can see there's a counterclockwise. It starts from 1 to 8, and we imaged it at 3 tracks going from the inside of the disk to the outside of the disk, totaling in 96 measurements total. And each image was 1 by 1 micron, consisting of 512 by 512 pixels. And the amazing thing is that these 96 measurements took only 2 hours. That included site navigation. And of course, if you're so quick, then it allows you to repeat these measurements, which even further increases your data confidence. On a conventional AFM, these images easily take your whole day, and I mean a long day to acquire. So a long day versus 2 hours is quite an improvement. And then when you have such a bunch of data, of course, you do have a lot of confidence, and you can get the information you want out of it. So what we see on the top is the raw data displayed as roughness on the vertical scale versus the inner, middle, and outer track here on the x-axis. And then we can, of course, start to find geometric dependencies. When we look at the left, we plot simply roughness versus angle, and we can see there are a few variations, but there's no clear trend visible. So versus angle, that sample seemed to be quite consistent. But when we plot the roughness versus radius, we can see a clear dependency indicating that there is definitely a change in the sample when you look at it versus the radius. Now, of course, you have to do the blind test, so to speak. You have to look at if my roughness suddenly goes down, is maybe my tip wearing out? So so we also plotted the average roughness to get an idea on the tip wear, and we can clearly see here that the tip is actually not wearing at all for that experiment. So further verifying that the data are indeed valid, and there is a roughness versus radius dependency on that sample. So again, from data storage, but just as an example how these measurements can help you to better understand your sample, and then of course change your process to optimize it. Now let's go away from OLEDs to high brightness LEDs. So gallium nitride LEDs. So a stack of a gallium nitride LED is shown on the left here, and they're often they're made on patterned sapphire substrates. So why is that? So you have a problem on high brightness LEDs with total internal reflection, and that amounts the amount of light that can be extracted from these devices. And the one of the ways to mitigate that is to pattern the sapphire substrate underneath, and these patterns exhibit basically a dense pattern of microscale bumps, and they do two things. They reduce crystal dislocations, and they also improve the emission efficiency by reducing these internal reflections. And of course, for proper performance, it is important to understand these patterns properly, and you need to inspect them for a variety of parameters such as uniformity of diameter, their pitch, their height. The sidewall angle can be quite important, and then of course the roughness in between these bumps can play a significant role. And what you get in terms of an image is shown on the left here. You see there's like a 6-point-something micrometer scan of one of these pattern substrates, and you can see in this case these bumps that form the PSS structure. There's a variety of these shapes depending on who makes them, and we will talk about that a little bit later. So the solution we employ for looking at on the AFM side, we employ for looking at these PSS wafers as the dimension Edge-PSS Automat. A look inside the Automat system is shown on the left here. We can see the AFM head, and below it we see a wafer chuck holding 9 of these typically 2-inch sapphire wafers. The stage, of course, motorized to accommodate a variety of samples and to address locations on these samples. Programmable, you can set recipes to determine where on these samples you want to take images and how many images you want to take on these samples. And it's quite fast. I mean, the imaging time is less than a minute per site. Again, because it's an AFM, you get highly localized data, and an example I've shown on the left here where you have a PSS structure, but when you look really carefully, you can actually see some defects on some of these PSS bumps. And again, that's the advantage of having an AFM and giving you nanoscale resolution at the same time. The software on the Edge-PSS Automat is, of course, also different than your normal research AFM software. It is greatly simplified to allow a operator to run the system without previous knowledge of AFM. And the user interface is shown on the left. You really basically see that there's a start button indicated by the green arrow on the lower right, and a stop button indicated by the red hand on the lower left. And that's all the operator. The operator doesn't have to adjust any parameters. That's all set by a supervisor, which has access to the system versus after typing in a password. The system generates automated reports. Again, the structure of these reports can be tailored. There can be long reports, there can be short reports, and an example of a short report here is shown on the right, where we basically only get the width, height, and the pitch of these PSS wafers analyzed. And then the system automatically indicates if a wafer passed or failed a set criteria by the supervisor. So a very, very simple system to run your data. Now, Bruker not only has AFMs, we also have fantastic 3D optical microscopes that we develop and produce for a very long time. And of course, these 3D optical microscopes are also great tools in production environments, such as analyzing PSS. So how do they work? So it's basically an interferometer, as it's shown on the left side here. And interferometers, as you know, are capable of measuring heights with very great precision. And other than AFM, where AFM is a serial imaging mechanism, this is an optical microscope, so it's a parallel imaging mechanism. So it's inherently fast. So the microscopes use special objectives to produce the height of your sample. They scan the optics vertically so that your sample is passed through the actual focal plane, and then the software calculates the height information and plots them accordingly from the focus scan data. And then two typical data sets from the PSS world are shown on the right here. The pre-PSS photoresist shown on the top, and then the PSS structure is shown on the lower right. Great tools for imaging and analyzing pre-PSS photoresist. You see the photoresist depicted on a sapphire, a corresponding SEM image, and then of course the image from the Contour GT, one of our state-of-the-art 3D optical microscopes. And again, they are fast, non-contact measurements, so your measuring system never contact the sample, and of course there's no effect from the sensor shape because it's an optical tool. We can not only look at the photoresist, we can of course also look at the PSS patterns itself. And I mentioned already there are a variety of different patterns, and 3 of them are shown here. We have on the left, we have dome patterns, we can have pyramidal patterns, and we can have cone patterns. And the 3D microscopes accurately reflect that shape. Because they are parallel, of course, imaging is quite fast, about 7 to 10 seconds or so per site. They are low-cost systems, but still have quite enhanced features such as enhanced data processing and objective stabilization hardware for high fidelity of data built in. Then let me just plug in a new tool that we have coming up here. It's an MOCVD epi characterization tool. It's meant to support production of MOCVD systems, which is metal organic chemical vapor deposition systems, and it will provide correlation to the deposition process and can be used, of course, as a watchdog to ensure consistency of your process. And it will be available in fall of this year. So we conclude our webinar here. We have shown you that nanoscale surface metrology of crucial OLED components is possible with AFM, and AFMs are great tools in order to perform these tasks. We have shown that PeakForce tapping can be used for repeatable, reliable results, and that electrical characterizations with PeakForce Kelvin or tuner measurements can be carried out and are indeed very useful to perform. We have an automated tools for the analysis of LED production parameters. We can use the FastScan or the Edge-PSS for high productivity. And of course, we have our 3D optical microscopes for fast, accurate measurements, especially on the pre-PSS photoresist measurements. Thanks for your attention, and now we are open for your questions.
So here's an interesting question. What physical parameters of semiconducting films can be extracted from scanning surface potential Kelvin probe data? Things like carrier concentration, conductivity type, band gap, work function.
Yeah, that's a good question. So for all these measurements can be carried out, of course, with the AFM. Kelvin microscopy gives you work function differences, and I think I've shown you 2 examples with it. Carrier concentration is not directly accessible with Kelvin microscopy, but if you want to look at carrier concentrations, you can look at either scanning capacitance microscopy, or you can look at scanning spreading resistance microscopy. Both of these methods are available on our AFMs.
Can you comment on the requirements for oxygen and water control for making accurate KPFM measurements? Does a person need a glove box to improve this?
Again, a great, fantastic question. The answer is yes and no. The water layer, if there is a water layer on your sample, of course, it will affect somehow your KPFM measurements. That might be critical for a specific application, that might not be critical for your application. Now, we do offer actually a glove box with a 1 ppm environment for our dimension icon and multi-mode instrumentation in order to perform such measurements. And if you have a system that you want to look at, please contact us offline, and we are more than happy to talk to you about that specific application.
Are there any standards available for KPFM? calibrate the probe?
No, what's done with a probe is basically you apply a known potential. I mean, there are samples, of course, and you can know these work functions. To my knowledge, there's no official standard available yet.
In working with PeakForce Tuna or PeakForce KPFM, can you measure the nanoelectricity in the liquid in the presence of an electrolyte?
That's an application that of course requires. Here's the problem when you do electrical measurements in an electrolyte. Your electrolyte will also conduct. So for these measurements, you basically need an isolated tip. So in general, no, not without a specific tip for this specific application.
And our final question. Is it possible to avoid parasitic surface charge on low conductivity surfaces that give work function artifacts in KPFM?
I'm not exactly sure if I understand that question correctly. Let me think about that a little bit, and I will answer that question in an email to you.
All right, well, I think we greatly enjoyed that topic. Appreciate you for presenting that to us, and appreciate all the attendees for their attention and their questions. With that, we will end the webinar. Thank you very much.